Okay, go ahead and take out your notes from yesterday's video over the introduction to stoichiometry. Now, we're going to start out here looking at a balanced chemical equation. What does a balanced chemical equation tell us? Well, obviously, it tells us the elements that are involved and how many of each element we have. Okay, so it tells us the elements and how many we have. It can tell us the mass, the moles, the particles, the volume, the density. Remember all the flux capacitor stuff that we can learn from a balanced chemical equation. Okay, so that moles, mass, representative particles, volume, density, all of that stuff is dealing with the flux capacitor. So what we are going to do is this stoichiometry is going to take balanced chemical equations and flux capacitor materials and put them together. So it is going to be a quantitative study. We're going to be dealing a bunch with numbers. So if we look at our learning target is to calculate the actual yield of a reaction given the reactants. So we could possibly just say, okay, you've got 2 grams of one reactant, you've got 5 grams of another reactant. Tell me how many products you're going to get. Well, you should be able to predict the reaction because we just got done doing that. And then you should be able to do conversions to get from that reactant to the product by the time we're finished doing this. Now, success criteria that we're going to need for today. Obviously, we need to have a balanced chemical equation. And if we have that balanced chemical equation, we're going to do something new, which we call the molar ratio. That's the big thing that is new for us with this video, molar ratio. We're going to use the balanced chemical equation and the molar ratio to convert from one substance to another. It could be from a product to a reactant. It could be a reactant to a product. It could be a reactant to a reactant. So we are going to use those values to make some conversions. So the very first thing we're going to do today is we're going to go from moles to moles, the very top one. But if you look at this particular slide, okay, we should be able to, by the time we finish, go from moles to moles, from mass to moles, from moles to mass, from mass to mass, from mass to volume, volume to mass, and volume to volume. So we're going to, and I'll refer to these, like today we're going to go mole to mole. It's a mole to mole problem. Okay, later on, I think next week we'll be doing mass to mass. Okay, so that's how I refer to these specific types of problems, just like this. Okay, so we're going to do this top one today, mole to mole. What I would like for you to do is go ahead and copy this example into your notes, and then we will work this example. I was nice with this one because I gave you the entire reaction. It says aluminum reacts with oxygen to form aluminum oxide. Find the number of moles of aluminum reacted if 1.57 moles of oxygen are reacted. Now, the very first thing we need to do with this is we need to get a balanced chemical equation. As I said, I gave you all the materials involved. So I have aluminum. It is reacting with oxygen. Remember that oxygen's a super 7. So my aluminum reacts with oxygen to form aluminum oxide. Aluminum's a 3 plus, oxygen's a 2 minus. So there is my skeleton equation. Once again, knowing how important being able to write formulas are. I've been preaching that. I've been preaching it. It's important to be able to write these formulas ever since nomenclature. So I look at this. I do not have a balanced equation, do I? I need to balance this, and I need to get this oxygen here to an even number. That gives me 6 oxygens, and then I'm going to have 4 aluminums. So I now have my balanced chemical equation. Now, when I'm dealing with the molar ratio, I'm dealing with the coefficients. So I'm going to look at the 4, the 3, and the 2. So if I have 4 moles of aluminum, it will react with 3 moles of oxygen to produce 2 moles of aluminum oxide. So when I'm looking at this to answer this specific question, okay, it says that I have 1.57 mole of oxygen, correct? Now, I'm going to use my molar ratio, okay? I'm going to use my molar ratio, because all I need here is right here. I'm going to use my molar ratio, and it's just very similar to what we've been doing with the molar conversions. I'm going to set up a conversion box. I want moles of oxygen right here to cancel. So where am I going to put that? On the bottom, right? So I have 3 moles of oxygen. Well, what am I trying to convert to? I'm trying to find moles of aluminum. So 3 moles of oxygen react with 4 moles of aluminum. Now, once I've done that, I get my moles of oxygen to cancel, so my label is going to be moles of aluminum. Now all I need to do is my math. So I take the 1.57, multiply that by 4, and then I divide that value by 3. I multiply on the top, I divide on the bottom. It gives me a number, and I need to go back and look. I need 3 significant digits, so it gives me a number of 2.09 moles of aluminum. So what I've done here, in the big picture, folks, is I've been given a value of moles of oxygen, and I have converted that value using the molar ratio into moles of aluminum. That's the very first step of all these problems. We have to know, okay, we have to know how to get a balance or a molar ratio from a balanced chemical equation. Any questions thus far on this? All right, now go ahead and copy this example into your notes, and then we will work it. Now, this is a beautiful one because I just give you the reactants. So aluminum reacts with iron 3 oxide. Find the number of moles of aluminum reacted if 2.43 moles of iron 3 oxide are reacted. So why this is so beautiful is because we have to use all of our knowledge of balancing chemical equations and reaction predictions. Because I'm going to start off, I have aluminum, and it is reacting with iron 3 oxide. Now, I look at that, I have to identify what type of a reaction this is. Correct? So what type of a reaction is this going to be? A single replacement. Excellent. So I have to look and see on my activity series, will aluminum replace iron? Okay? Will aluminum replace iron? What do you think? What do you think? Ashton, I see you have your activity series out. Will aluminum replace iron? Absolutely. Aluminum's more active. It's higher. So I'm going to then get aluminum oxide and iron. So I've predicted the single replacement reaction. Now I need to balance this. And as I'm looking, my oxygens are okay. I need to have 2 aluminums and I need to have 2 irons. Now I should have a balanced chemical equation, correct? So I've predicted a reaction. I've balanced an equation. Now I need to do all that before I can even start my problem. Now I can get into my problem. And it states that find the number of moles of aluminum reacted if I have 2.43 mole of iron 3 oxide. So I have 2.43 moles of iron 3 oxide. I need to set up my conversion box, and I'm going to use, once again, the molar ratio. Okay? What do I want? What do I want, Trista? What do I want on the bottom? 1 mole of Fe2O3. Because when there's nothing there, it is a 1. Okay? What am I going to put on the top here, Ella? 2 moles of aluminum. I cancel my moles of iron 3 oxide. Gives me a label of moles of aluminum. That's what I was looking for, right? So I'm going to take that 2.43, multiply it by 2, divide by 1. So that's going to give me 4.86 with 3 sig figs. So if I have 2.43 moles of iron 3 oxide, I need to have 4.86 moles of aluminum to react with that. We okay thus far? All right, we got one more to do, one more example to work. So go ahead and copy this example into your notes, and then we'll roll with it. Potassium phosphate reacts with magnesium chloride. Find the number of moles of magnesium chloride reacted if 5.0 moles of potassium phosphate is reacted. Once again, I need to start with a balanced chemical equation. So I need to predict my reaction. Potassium phosphate will react with magnesium chloride. So I need to decide what type of a reaction this is. Anybody got any ideas? Ashton? This is a double replacement number 1. 2 salts are reacting. So what I'm going to do is I'm going to flop my cations. So it's going to give me KCl and magnesium phosphate. Now, I need to check my solubility chart. Potassium chloride is soluble. Magnesium phosphate is insoluble. So have I hit my parameters that I need for this reaction to occur? Absolutely. So this reaction will occur. Now I need to balance. I'm going to start with phosphate. Balance my phosphate. That gives me 6 potassium. And if I put a 3 right there, I'm balanced nice and easy, aren't I? That should be balanced. Agreed? Okay. Now I can get into the meat of the problem, the numbers. So I have 5 moles of potassium phosphate. I want to find the number of moles of magnesium chloride. So I can see based on my molar ratio, 2 moles of potassium phosphate will react with 3 moles of magnesium chloride. My moles of potassium phosphate cancel. It's going to leave me with a label of moles of magnesium chloride. So I'm going to take 5 times 3. What's that going to give me? 15. And 15 divided by 2 is going to give me 7.5. And I do have 2 sig figs, so that's good. That's 7.5. Put my box around her. Final answer. So if I have 5 moles of potassium phosphate, I need 7.5 moles of magnesium chloride to react with that 100%.